All right, finally we get into examples of actually determining the value of a definite integral. Now, we're going to kind of cheat a little bit in this video, and we're going to look at very simple definite integrals that we can evaluate using just some basic geometry. Later on, we'll get into more of the calculus behind evaluating definite integrals. But for now, we're going to evaluate definite integrals using geometry. So you can see I've got my graph paper set up here. You may want some as well for your notes if you're taking notes. But basically, what I want to do in this example is use the graph of f to evaluate each integral. Okay, so I'm going to draw a graph of this function f, and then we're going to use it to evaluate some integrals. So let's get started on drawing the graph. So I'll set up my y-axis over here on the left side of the graph. So there's my y-axis. And then I'll set up my x-axis kind of in the middle of the graph paper. In fact, let's call this a t-axis instead, just so we can see that you can use different variables when doing your integral. So that's t, and then this would then be f of t as your y-axis, of course. So let's set up a scale on the t-axis and a scale on the f of t-axis. I need to go up to 2 and down to -2 on the y-axis, so I'll call that 1 and I'll call that 2. So -1, -2, okay? So we've got our y-axis set up. Then we need our x-axis. I need to go from 1 to 6. So let's say that that's 1, 2, let's count by 2s, 3, 4, 5, and 6, okay? All right, so now we've got our grid set up, and let's start to graph the function f. Let's start at the point 1, 1 with a closed circle. And then we'll go over to the point 3, 1 with another closed circle. And then we'll have a closed circle at 2, 2 as such. And what I'm going to do is connect those 3 points with the top half of the circle. So, and I'll try to do that. I'm going to stand in front of it because it's easier for me to draw. Still be pretty bad, but we have the top half of a circle there. And then from that point, we're going to go through the point at 4, 0, 5, -1, and 6, -2 is where the graph will terminate. And so I'll connect those points with a straight line. So I've got a straight line from the end point of my half circle to the end point at 6, -2. Okay, so this is our function f of t. Now, let's evaluate some definite integrals with this function. So, the first definite integral that I want to evaluate is the definite integral from 3 to 6 of f of t dt. So again, remember the dt indicates that our independent variable is t and that these are t values, okay? And so to evaluate this definite integral, in this case, we need to think of it as the area under the curve from 3 to 6. So if we come over here to our graph, we're looking for from 3 to 6, what's the area? So we're breaking our graph into this from 3 to 6, from here to here. We need to break it into 2 different areas. This area here is a positive area, while this area here is a negative area. So the first thing we're going to do is we're going to split this integral apart. We're going to split this integral apart to be the integral from 3 to 4. the integral from 3 to 4 of f of t dt plus the integral from 4 to 6 of f of t dt. Okay? And so that's kind of that's a general property of definite integrals. You can take and split this at any value between and separate it into two integrals that add together. So that's kind of neat. Now that I've got my two integrals split apart, my two regions separated, I just need each of them figured and added together. So let's come back to the graph of the function and see if we can figure out the integral from 3 to 4. Well, the integral from 3 to 4 is just this area of this triangle, which we can figure using geometry. So we've got the area of a triangle is 1/2 times the base length, which is 1, times the height, which is also 1. So that area, that integral, that definite integral, is just 1/2. Plus, we do the same for the integral from 4 to 6. That's this area. Be careful here because this area is below the t-axis, so it's a negative area, but it's still a triangle. But now we've got negative 1/2 times the base, which is 2, times the height, which is also 2. And that height is precisely why it's a negative area. You could say it's a -2 height and not put the negative in the front. Either way is fine. So we've got negative 1/2 times 4, so that's -2. So that integral here is the negative area, -2. And so added together, we get 1/2 minus 2, which is -3/2. So this integral from 3 to 6 of that function is -3/2. So you can see how it outputs a number that represents area. Okay? So that's the first integral we will do. Let's do one more, just for good measure, and look at example B. Example B is the integral from 1 to 2 of f of t dt. Okay? The integral from 1 to 2 of f of t dt. And so in this case, what we're looking for is the area under the curve, which now is going to be this area right here under half of this top circle. And so we need to, using geometry, what we're going to have to do now is we're actually going to have to split it differently. Because what I have is a square on the bottom plus 1/4 of a circle. Now, I'm not going to split my integral because I'm not cutting this region horizontally via x values. I'm actually cutting it vertically to use geometry. So what I'll do is find the area of the quarter circle, add it to the area of the square, and that's going to be the area under the curve, giving us the value of this definite integral. So this area right here is 1/4 of a circle. So that's going to be 1/4 of pi r squared. The radius of this circle, you can see, is 1. So we get 1/4 times pi times 1 squared. That is the same thing as pi over 4. Plus, I need to add on the area of the square, which is 1 unit by 1 unit. So this area is 1. So the value of our definite integral here, let me get the lid on my marker. The value of this definite integral is the area of the quarter circle plus the area of the square, which is 1. And since they're not like terms, this is in terms of pi, this is not, we don't need to add those together. And so that is the value of this definite integral using geometry again. Again, later we'll look at specific functions where we don't have a graph and we still evaluate definite integrals. But for now, we can do it with some basic geometry.